Lagrange multipliers are used in a technique by which we can optimize a function f, which we're going to call an objective function, subject to an equation g equals c, which we call a constraint. An example of a problem that would use Lagrange multipliers would be find the maximum area for a rectangle inscribed in the ellipse x squared over 3 squared plus y squared over 4 squared is equal to 1. The equation of the ellipse is the constraint. And it's actually a level curve of a function gxy equals c. And in this case, g of xy is x squared over 3 squared plus y squared over 4 squared. 1 on the other side of the equal sign is just a particular value of c. Now, as far as what we're trying to optimize, in this case, we're trying to find the maximum area for a rectangle. And so the function f that we want to optimize should reflect that, the area of a rectangle. And in this case, our objective function, f of xy, is equal to 4xy. I'll talk a little bit about where the 4 comes from in a minute. You may already have an idea. I'll get into that in a minute, but first I'll say that the way these problems are worded in our textbook are mostly maximize f of xy equals 4xy, subject to x squared over 3 squared plus y squared over 4 squared is equal to 1. I'm presenting this as the maximum area for a rectangle inscribed in an ellipse so that you have kind of something to hang on to with this. And in order to help us wrap our minds around this, I'm going to give you a diagram from a textbook that is not ours. On the left, we have the ellipse, x squared over 3 squared plus y squared over 4 squared is equal to 1, inscribed inside of which is a rectangle. And as you can see, there's a point identified in the first quadrant, xy. And x is the distance from the y-axis, and so the horizontal width of this rectangle is going to be 2x. The vertical height of the rectangle is going to be 2y because y is the distance from the x-axis, and that's why this area is given as f of xy equals 4xy. Over on the right, we have a different way to look at this. There's the ellipse, and it's given as the constraint. G of xy equals x squared over 3 squared plus y squared over 4 squared is equal to 1. And there are several level curves of f of xy is equal to 4xy. Now I'm going to back up a little bit because I told you that the equation of the ellipse could be thought of as a level curve for the function g. And I was saying that to let you know how we're looking at g of xy. I mean, it's a function of x and y. But here, when it's equal to 1, it becomes an equation, and so not really subject to change. The function f of xy is a function. And for any particular pair of x and y, we get an output that this author is going to call k. We recognize z equals 4xy as a hyperbola, or I should say a hyperbolic cylinder. And these curves are just the intersection in the xy plane of a portion of the hyperbolic cylinder. And we see that there are values for k of 72, 56, 40, and 24. And the curve of that, I'll just say it's a hyperbola. The curve of the hyperbola that's just touching the ellipse represents the k value that will maximize the function 4xy. And the idea of maximizing the function f is that we want the biggest value of k such that a point on that curve shares a point on the ellipse. Now we can imagine a value of k where the curve would intersect the ellipse twice, but that wouldn't be the biggest value of k where the point is shared between the two curves. So that k is what we're after. We can see in the picture the answer is going to be 24. I mean, that's a spoiler alert. At the end of this problem, we're going to say, hey, 24. But we're going to go over the process by which this occurs. Now, as the basis for this technique, we're going to consider a tangent line to both the level curve 4xy equals 24 and the constraint. And here we have that tangent line. It's the tangent to g equals 1 and one level curve of f. The tangent line to a curve is orthogonal to a gradient vector of the curve. And so here I have the vector, the gradient vector del f. And for g at that point, there's also a gradient vector del g. Whoops, I wrote that as a delta and not a del. Now these gradient vectors are orthogonal to the tangent line. Since they're both orthogonal to the same tangent line, they must be parallel to each other. In general, we can say that a vector u is parallel to v if and only if u is a scalar multiple of v, and so u equals cv. And here we have that del f is parallel to del g, and that is true if and only if del f is equal to lambda times del g for some lambda in the real number system, or for some real number lambda. That equation there, del f equals lambda del g, that gives us the technique that we're going to use, believe it or not. The lambda is what's called the Lagrange multiplier. And I'll point out right now that throughout this section, we're going to assume that del g is not equal to the 0 vector. With that as background, let's see how this process works. F of xy is equal to 4xy, and so del f is equal to 4y, 4x. G of xy is x squared over 3 squared plus y squared over 4 squared is equal to 1, and so del g is equal to 2/9 x, 1/8 y. If del f is equal to lambda times del g, then the vector 4y, 4x is equal to lambda times 2/9 x, 1/8 y, and that leads us to a couple of equations. Equating I components and distributing lambda will give us that 4y is equal to 2/9 x times lambda, and equating j components will give us the equation 4x is equal to 1/8 y times lambda. Let's call those equations 1 and 2. And because we have three variables, x, y, and lambda, we need a third equation. The third equation is going to come from the constraint. So the third equation here is x squared over 9 plus y squared over 16 is equal to 1. This is now a system of equations, 3 equations and 3 unknowns. But as we're looking at this, I'll make a note right now. We want x and y. Our goal is not to find lambda. Sometimes we may find it by kind of accident or along the way, but really we need to optimize a function, and so we need to know what x and y are. Now that we have this set up, let's try to quickly work through this. If I take equation 1 and solve it for lambda, I will end up with lambda is equal to 18y over x. Likewise, with equation 2, solving for lambda will give us lambda is equal to 32x over y. Having solved for lambda, we have two expressions that are both equal to lambda, so they must be equal to each other. So 18y over x is equal to 32x over y. And that equation, after cross-multiplying, simplifies to 9y squared is equal to 16x squared. Now, we've done a good thing here. We've gotten rid of lambda in our equation, and that's cool because we need x and y and not lambda. But now in order to solve for x and y, I need to join this with an equation that has only x and y in it, and that's where the constraint is going to come in. If we solve for either x or y, we can substitute in the equation of the constraint. And I'm going to go ahead and solve for x, x squared. And x squared is equal to 9/16 y squared. Plugging that in place of x squared in the constraint equation gives us 9/16 y squared over 9 plus y squared over 16 is equal to 1. I will let you verify that that gives us that y is equal to plus or minus 2 times the square root of 2, and that plugging that value for y into the constraint equation will also give us that x is equal to plus or minus 3 divided by the square root of 2. We have our values of x and y. We're going to put them into our function. F of x, y at the beginning was 4xy, and our picture originated with xy in the first quadrant because we were talking about the area of a rectangle. So if we look at f of 3 over root 2, 2 square root of 2, that's a point in the first quadrant, and it evaluates with 4xy to being 24. That, of course, agrees with what we thought when we saw the pictures to begin with, right? Remember, we were kind of told here, hey, k is going to be 24 with k equals 4xy, but we aren't going to have that picture usually. As an aside here, we can say that f of, for instance, negative 3 over square root of 2, 2 root 2 is equal to negative 24. Now, we don't care about that in the context of the area of a rectangle, but in terms of just a general, where are we here? Optimize instead of maximize, f of xy equals 4xy subject to the equation of the ellipse, we would say the maximum is 24 and the minimum is negative 24. And you can see what would happen if you plugged in negative 3 over root 2 and negative 2 root 2. You'd get the same value of 24. And then switching the plus and minus so that we had f of 3 over square root of 2, negative 2 root 2 would also give us negative 24. We'll wrap this up by saying the maximum value, or the maximum area rather, is 24.